now that you've had a chance to do the transition matrices, let's see what you got. So my transition matrix that I got from B to B prime is negative 22/75, 46 75, 11/15, 2/15, negative 11/15, 2/3, negative 71/75, negative 22/75, and negative 2/15. And finding the transition matrix from B prime back to B, which notice is the inverse of this guy, and notice that he's pretty special. Okay, so what are some special things here with our P and Q matrices? Well, once again, we know that P is equal to Q inverse, and P inverse is equal to Q, of course, because one goes one direction, the other goes the other direction. Okay, and we had orthonormal bases, which was actually something pretty special. So if we take a look here on our calculator, I went ahead and took the row vectors here, and I found their magnitudes, technically magnitude squared, and found out that each of the row vectors has a magnitude 1. You can double check that the row vectors are also orthogonal. So again, the rows are orthogonal, rows and columns of P and Q are orthogonal. And they're each length 1, as we just saw here. So we combine that all into one word. We call that orthonormal. Okay, that's cool. And why was that special? Why did that happen? Well, we started with 2 orthonormal bases. B and B prime. Remember how we said that those guys were orthonormal at the start of this activity? Okay. So that leads us to something that we are now going to finally introduce here, and that is the idea of an orthogonal matrix. And an orthogonal matrix is any matrix where his transpose is equal to his inverse, or his inverse is equal to his transpose. And you'll notice that P being the inverse of Q and vice versa, and notice that these two matrices are simply the transpose of each other. So that's pretty cool. Another thing that's cool is that the determinant of an orthogonal matrix will always be equal to 1 or negative 1, so I'll write plus or minus 1. Okay. And again, if it's an orthogonal matrix, the rows will be orthonormal. And the columns will be orthonormal. Okay. And another thing is, if we take an orthogonal matrix, that's another thing that I'm going to mention here. We say that the matrix is orthogonal if this is true, but if I controlled the world, I wouldn't call it an orthogonal matrix. I would call it an orthonormal matrix, but I don't control the world, and so we're going to go with the notation they've already, or the name they've already given, orthogonal. I prefer orthonormal matrix because the rows are orthonormal, the columns are orthonormal, and that helps us see that the determinant is going to be plus or minus 1. And the inverse of an orthogonal matrix is orthogonal. The product of orthogonal matrices is orthogonal. So he has all kinds of cool properties. So the product of orthogonal matrices is orthogonal, and they preserve length, as we saw on the first page. So if I take and find the coordinates with respect to one basis, and I multiply by an orthogonal matrix and find its length using the same inner product, I get the same length, and we saw that over here too. Cool. All right, so which of our matrices that we found above are orthogonal? Well, in the 2 by 2 case, we saw that we had 117 over 125 and 44 over 125 and negative 44 over 125 and 117 over 125, and his transpose, of course. And we just saw in our 3D case, let me write it a little bigger here. This matrix was also orthogonal. And negative 71 over 75, negative 22 over 75, and negative 2 over 15. Be careful of that one. So my 1s and my 7s started to look a little similar on the last page. Okay, so now what I want to do is talk about some of the implications of these orthogonal matrices. So let me go back up to our original system here. So we had U1 and U2. U1 was 0.6, 0.8. So 0.6, 0.8 would be this vector, and so I'll name him U1. U2 was negative 0.8, 0.6, which is this guy. And if you're careful, you'll notice that here's our I vector and our J vector. You notice that U1, U2 just happens to be a rotation of the I and J vectors by this angle theta. Cool. All right, well, what about V1 and V2? Well, V1 was 0.28, 0.96, which would look about here. So here's V1. Okay, and V2 was negative 0.96 and positive 0.28, which would put us about here. So there's V2. And notice that this is, once again, just a rotation of the I and J vectors, but now by a new angle I'll call phi. Okay. So U1, U2, and V1, V2 are merely rotations of each other. Okay. In fact, to get to V1, V2 from U1, U2, I would find out what phi is and subtract theta, and then just rotate these red vectors just a little bit more until they lined up with the V1 and V2 vectors. Okay. So what I want to do now is look at the three-dimensional case. So let me screen share that one. And here he is. Okay, so I've gone ahead here in black, I've got the I vector, E1, and you can see I've got my three vectors, U1, U2, and U3. Okay. And you'll notice that they happen to be just a rotation away from I, J, and K. So it's just like, because these red vectors do form an, if I can do this, you'll see it, an orthonormal basis. Okay. So those are our red U1, U2, and U3 vectors. Let's go ahead and show you the V1, V2, and V3 vectors, which again are just rotations of IJK. It's like taking a box that's got faces in the X, Y, YZ, and XZ planes, and then just rotating it a little bit about the point on the origin. Although with this one, if you'll notice, if I go from V1 to V2, if I'm using my right-hand rule, point my vectors in the direction of V1 and then turn towards V2, my thumb would actually point opposite V3. So this is what we would call a left-handed system, whereas the U1, U2, U3 is a right-handed system, because if you point your fingers in the direction of U1 and curl towards U2, your thumb on your right hand points up with U3. And so since we transition from a right-hand system into a left-hand system, going from the red to the blue, or vice versa, from a left hand to a right hand, not only does this involve a rotation, but it will also involve a reflection, which is pretty cool. And you'll notice that if I take the determinant of that transition matrix that we did for our 3x3 system, you'll get not 1, but -1, because he involves both a rotation and a reflection. Pretty cool. And that's chapter 6.